What did we do last week? Thought I said something else. What did we do last week? It's important because we're continuing it, so you better know. Integer programming. How many examples? What were they? Can you speak up?
The graph with the dots.
The graph with the dots.
Yeah. The one with 3 guys and 2 girls getting married.
How about 3 guys and 3 girls getting married? So old-fashioned. And? How many containers to take on the ship? So what did I promise for today? Nothing? Good. Let's try and solve something. Okay, let's try and solve that one. So that was the graph with the dots, if you like. In my world, every graph has dots, so. But then I don't do analysis. But there are graphs of functions, they don't have dots. They're scary. Okay, there are 2 kinds of algorithms for solving integer programs. Well, 3 kinds really, because there are 2 basic kinds, and then one which is created as a combination of the 2. I'm sorry as well. So 2 basic kinds of algorithms. The first kind is called branching algorithms. And the second kind is called kind of cutting planes algorithms or something like that. So today what we're going to do is go through the basic idea of branching algorithms. And next week what we're going to do is still finish branching algorithms, and then a bit later, so that you don't get bored with doing algorithms all the time, some formulations and a bit of Mosul, we'll move on to cutting planes algorithms. Okay, so just very briefly, the cutting planes algorithms, when you remember the picture we had, they're based on trying to find this kind of thing, which valid inequalities. That's for later. Where we're trying to cut off the space, which is the feasible solutions of the linear program without constraining the values to the integral. and you're trying to get them out without removing anything that's integral. And for the branching algorithms, they work in a different way. They try to split the problem into two different subproblems, or even more, and then solve each of the subproblems. And then for each of the subproblems, you have to find an optimal solution, and then then you look at which one is better of the two, and you take the better one, and that'll be the solutions. For example, in this situation, you can say, well, there's XA. So we can look at all the solutions where XA is 0 or 1, and solve and find the best one among them. Or we find the best one. This is the idea of branching. Split it into two subproblems, solve each of them, and then you find and you take the better of the two solutions. Okay, so example. Branching. What does it do? So as an example of what we want to do is we're trying to solve. We want to solve this problem where there are 9 decision variables. There is some objective which comes from the table that is in the handout. Oh, I didn't bring the handout, so if you don't have it, look at your neighbor's handout, please. It's the one from last week. It's an objective function, and there are some constraints, and all of those constraints are more or less the same. So they're saying that the sum of 3 decision variables is 1. And the meaning of them is that, so the first one says that Alice gets exactly 1 man, and Becky gets exactly 1 man. That's the reminder of what we did last week. How do we solve this? I don't know. Okay. Get this. Yeah. So I'll draw a tree which branches, and that's where the name branching comes from. So the problem we're trying to solve, I'll call it S. And that's the problem that we want to solve. Okay. That's the whole integer program that we have. But what's going to happen is we'll have 2 branches. And I don't yet know which is going to be the better one. So now the question is, how do we create the branches? For the moment, I picked one of the variables. The one I picked when I was looking at it was XAP. AB, AP. Okay, and XAP can either be 0 or XAP can be 1. There is no other option for XAP. It has to be either 0 or 1. So if we solve the problem where XAP is equal to 0, find the best possible solution of the whole problem subject to this condition. And then separately, if we solve the whole thing with XAP equal to 1, and then take whatever is better, then we'll have solved the problem. Do you agree? Good. That's the idea. Now, what do? I'll call this S not because it's not, because I want to call it that. Now call this one S1. And we can't really do anything, can't really do much here in this case. What we can do in this case, however, is that if XAP is 1, this will give us some other values. So look at, where are we? That constraint, the top one. See that constraint? So because XAP plus the other two variables is equal to 1, what does it tell us about the values of XAR and XAS? They have to be 0, because otherwise the constraint would be violated. So in this case, of putting XAP to 1, we know that XAR necessarily and XAS also have to be 0. And then similarly, we would have that XBP and XCP is also 0. Okay, because there's another constraint that says that XAP plus XBP plus XCP is 1. Now, how do we solve these two subproblems? The answer is obvious. So you're too busy copying. So we solve them by branching. So we can pick another variable. I've picked, for some reason here, I've picked XAR. So either it's 0 or XAR can be 1. And this gives me problem S01, and this gives me problem S00, S01. Okay. So in this case, we have XAP is 0, XAR is 1. We also, because of what the constraints were like, we need that XAS and XBR and XCR, they have to be 0 because of some of the constraints, in the same way as we said here. And, whereas here, I know that XAP and XAR are 0, but XAP plus XAR plus XAS adds to 1. So that means that XAS in this case has to be 1. Okay. I don't think there's anything else. And because XAS is 1, then XBS and XCS have to be 0. Yeah, that's what it is. Okay, now it's starting to be boring, but bear with me for another couple of seconds. We can also branch S1 into S10 and S11. And what I chose was XPR. So XPR is either 0 or 1. The natural question is, how am I choosing the variables whose values I branch, whose values I decide whether they're 0 or 1? No good answer. For the first one, it doesn't matter because they're all kind of the same, all symmetric. Second one, get some information if I choose something that has A or P in it. Because then I will have, so if I take something with A in it, the constraint that AP plus AR plus AS are 1 gives me some information. So AS must be 1. But it doesn't really matter. Okay, now we haven't finished this branch yet. So if XBR is 0, now XAR is 0, so XCR must be 1, I think. And you also get that XBS must be 1, and all the remaining ones will have to be 0. XAR, yes, B, BP, BS, XBR must be 0, CP, XCS must be 0. If we go through all the constraints that we have, you will have to conclude that this is the only possibility for all the variable values. And so you can now work out what the value of the objective is in this case. If AP is 1, and CR is 1, and BS is 1, and everything else is 0, this gives me 0.3, CR gives 0.9, and BS 0.6. From the table, you have the table. So adding them all together, I think you should get 1.8. Is that right? And in this case, you can also get the full solution. So XAP is 1, XAR and AS are 0, XBP and CP are 0, XBR is 1, and you also get that XCS has to be 1. XCR has to be 0, and something else has to be 0. In any case, you get these three, CS, BR, and AP. And that gives you the value of 1.9. Okay, so as an example of what happens, this is almost good enough. The question is now, what is the optimal solution of the problem S1? Wake up. Okay, so how are we getting all these things? Does anybody know how we're getting all these things? Well, nothing could be more obvious.
You follow it down.
Nothing could be more obvious. Okay. So how are we getting which things? Okay, you have your problem. That's the one that we started with. All the constraints, the objective, all the decision variables. Is that clear? Good. Now we split it into solving two subproblems. And I pick XAP because because it's the first one. It doesn't really matter which one I take. I've got it then, thank you. Yeah, I split it into two subproblems. If I solve both of these problems, then I can take the best solution, and that gives me the option. That's the idea. So I split it on XAP. Doesn't really matter which variable I take. I've chosen XAP. But there is one possibility for XAP is that it's 0, and another possibility is that it's 1. It can't be anything else because the formulation tells you so. Okay? Is that clear? Good. Now, if XAP is 1, there is this constraint, this one. XAP added with two other variables has to be 1. Now, each of them is either 0 or 1. So if this is 1, both of them two have to be 0. That's how I get in there XAR and XAS is 0. And somewhere there at the bottom, oh no, not at the bottom, actually yes. So here there's this constraint. XAP plus them two has to be 1. So if XAP is 1, these two things have to be 0. Okay? So that's how I get my XVP and XCP is 0. Okay? Is that clear now? And this is everything. I can't get any other values for sure from setting XAP to 1. It only appears in those two constraints. So, still some information from knowing that XAP is 1, but not quite everything. So, still don't know the values of everything. But again, there will be several options. So I decided to split one. Why not BR? Now I split and I look at two possibilities. The one where XBR is 0 and the one where XBR is 1. Yeah.
You simply haven't got like XAR.
Yeah, you certainly can't choose XAR because XAR you know for sure it's 0, so you can't split it into 0. I think so. You know 5 of them, so there are 4 variables left, and it doesn't really matter which one you pick because they're all kind of natural. And when you do split it, then again you go, right, XBR is 1, and everything else with B has to be 0 because Becky can only marry one person. That was the point of these constraints. B is already 0, we already know that, but BS also has to be 0. And then everything else with R has to be 0 as well. So CR has to be 0, AR will know it's 0. But then there's XCS left, and you know that it appears in some constraints where everything else is 0, so necessarily has to be 1. False. It's not constraint, and I think XCB and XCR we've already said that. Maybe not XCB. No, but XCS. Let's have another look. Oh yeah, because AS is 0, BS is 0, we just said, but AS plus BS plus CS has to add to 1, so CS has to be 1. Is it any better now?
Could you write that the other way around?
BS first.
Yeah. That was one. You want to.
Oh, if BS was BS to be 1.
Yeah.
No, I can't have BS 1 because I said BR is 1. BR plus BS plus B have to add to 1. So from BR being 1, necessarily BS is 0. From BS being 0, necessarily CS is 1. So I should really put this above that. But not XBS being 1. You can't have. Okay, so really the idea is that when I'm branching, that I'm making a choice freely. All these that are in the box, they're enforced by the choice I've made. But when I said XAP is 1, then those 4 variables have to be 0 from the constraints. When I make my choice that XBR is 0, then everything else follows from the constraints. XBR is 1, everything else follows from the constraints. Okay, any more questions? Is everybody happy now? Who's happy? Who's sad? A bloody simple idea. You make your choice. From the constraints, some other things will follow. If not everything, you make another choice. From the constraints, some other things will follow. And if not everything, you make another choice. But here, everything is already determined in both of these cases. So if everything is already determined, we can plug it into the objective and get the value of the objective. Yeah, and these values, all of them, we can plug into the objective and get the value of this objective. So the best solution here is there's only one solution, and it has objective z. It's 1.9. And here there's only one solution, and the value is 1.8. So what is the best solution for this problem? 1.9? Yes. So the best solution here has value 1.9 because it's the right one. Right? Now in these two cases, we still don't know all the values. So I split it further. Well, I would have to split it further. And I'll only really follow through one of the cases. So here I've decided in my example that I will take xbp, and either it can be 0 or it can be 1. And here I can take xbp, and either it's 0 or it's 1. So in this case, where xbp is 0, I get a problem which I call S000. I've made the box too small. Okay, now, again, xap is 0, xbp is 0. But if I add xap, xbp, and xcp, they have to give 1. So xcp must be 1. And I have xps is 0 and xbp is 0, so xbr must be 1. And xcr therefore has to be 0. You happy with that? Yeah. It's easy to remember the constraints. It's always everything with A added together has to be 1. Everything with B added together has to be 1. Everything with C added together has to be 1. Everything with R added together has to be 1, and so on. Okay. So in this case, we've already determined everything, and we get that the value of the objective is 2.3, I think. That seems plausible with your table? And here, I'm not going to do all the values. I'm just going to say that, and it's up to you to check in your own time. Here, I would get 2.2, and here I would get 1.9, and here I would get 1.9 as well. And so from this, we know that here the best solution is 1.9. Here the best solution is 2.3. How about it's not? Let's see. I shouldn't be asking questions. Everybody knows. I hope. Okay, and therefore here the optimal solution will also have. So we found an optimal solution. And it's the one that solves that problem, 0, 0, 0. So what is it? XAS and XBR and XCP are 1, and the remaining variables are 0. So XCP, XAR. So all of those are 0. And objective as value 2.3. that good now? So this is what happens when you're trying to solve an integer in code. It's quite it's not. But it's not so bad because we had 9 binary variables. So there are 2 to the 9th, which is 512 different assignments of zeros and ones to those 9 variables. So the most stupid way of solving that problem is to look at all 512 different 0 1s assigned to these x's and looking whether they satisfy the constraints and whether they have what the objective is. And we only had to do it for 1, 2, 3, 4, 5, 6 different assignments, not 512. So it's already so give you that it's not for a lazy person, but it's still much better than looking at everything. But there is an improvement. Do you want to know the improvement? There is improvement. There is a slight improvement. It doesn't necessarily always improve it massively, but it does improve it a little bit. And it's called a branch and bound. Okay, let's have a look at the following example. It's quite a simple example. Yes, to maximize, there's only 2 variables. 4x1 minus x2 is the objective, and the constraints are 7x1 minus 2x2 is less than or equal to 14. x2 is less than or equal to 3, and 2x1 minus 2x2 is less than or equal to 3. And x1, x2 are in z plus. Well, maybe I didn't say what z plus is. What is z plus? X1 and x2 have to be greater than or equal to 0 and integer. Okay. This is not an important example because it's important because not because it's important in the world, but it's important because we're going to learn the algorithm of it. I wanted to branch this. I could do one of the possible things that I can do is look at x2. x2 is 0, 1, 2, or 3. Can't be anything else. Can't be more than 3. Can't be less than 0. It has to be integer. So I could say solve one sub-problem where x2 is 0 or 1, and I'll solve another sub-problem where x2 is 2 or 3, and I compare the two solutions, and I take the better one, and that would be good. It's a possible approach to branching in this particular problem. And then I could branch again, and branch again, and branch again. This is indeed the idea of solving a problem like this, where the variables are not necessarily 0 or 1. Let's branch. But what is bound? Bound is the idea that it's the best way to tell you without confusing. If I somehow learn that one of my branches definitely does not contain the optimal solution in some way, then I just ignore it. The idea of simplifying work in the branching algorithm by bound. And the way how you can learn that some branch does definitely not contain the optimal solution is by having a bound on how good a solution that can be in that particular branch. So the idea is the following. I'll call this P. I might call it P. This is the problem we're trying to solve. And I'll do a problem which is like R, which is called R, which is the same as P, but x1, x2 don't have to be integers. You know how to solve R? Use simplex, for example. Yes. Why? Yes, it's just an LP. So R is just an LP because it's a linear program. Because it doesn't have anything else than the usual constraints of a linear programming. Okay. So you can solve it using the simplex method. So we know how to solve it. In fact, this is called the LP relaxation of that problem P. When you get an integer problem like this one, you get rid of the integrality constraints, but leave everything else in place. That's called the LP relaxation. So if you solve this by simplex, you get that x1 is 20/7 and x2 is 3, and the objective is 59/7. Does this give you any information about the optimal solution of P, the original problem we were trying to solve? Pardon? X2 is going to be 3, not necessarily. That's not the information that you get. But something else.
The objective can't be higher than 907.
Why not?
What's that?
Yes. Yes, you're right. But has everybody get the idea of that? Okay. But two problems, P and R. And P has more constraints. R has all these. P has all the same constraints as R has, but on top of that, x1 and x2 have to be integer. So you have fewer options for x1 and x2. So whatever solution you find for P will also x1 and x2 that satisfy the P will also work for R. Okay. So you can't get any. So you definitely can't get a better objective in this problem with the integrality constraints than you can get in the relaxed problem where you don't need solutions for them. So, quite right. Here we know, therefore, the optimal solution of P satisfies the objective is certainly not more than 59/7. In fact, because we know that the objective also is an integer, because x1 and x2 are integers, and 4 times x1 is integer, and minus x2 is integer, so that is also integer, so it can't be more than 59 divided by 7, I think is 8. And 3/7, so it can't be more than 8. Okay? So that's the idea of bounding things. We know that this in the whole problem, we can't have the optimal solution can't be better than objective value 8. Now, if we split it into two subproblems somehow, we're only going to do next week, and we solve one of the subproblems, and we find that there is a solution that has objective value 7, and we see that the bound for the other subproblem is 5, and we don't have to do anything in that other bound because we have the optimal solution. That's the idea of bounding. So turn all these ideas into an algorithm next week. Until then, you have a nice little, very difficult homework problem.